Hello, my name's Philip. We met last year in Addis for some spine teaching. This year we're going to try and teach mainly on spinal trauma, and we plan to have a cadaveric lab to teach some motor skills, but also some higher level learning. My name's Philip Sell. I'm from Leicester, which, as you can see from the map, is pretty much in the middle of England. The picture on the left shows me leading from the middle in the teaching group in Addis, which was, I have to say, really good fun, and I learned a lot from you guys. I'm not going to talk to every slide, but the important thing in considering biomaterials and bioengineering and the whole concepts is to consider the whole spinal construct. Often what we see from the industry is testing of a single individual item, and it's the whole construct that counts. This is a picture of the building of the bridge over the River Avon, as being built by Isambard Brunel, one of the great engineers. You can see the various forces at work. On the suspension columns there's a compression force, the cables give a tension force, and there's also a reaction force within them. This is quite a busy slide. It simply shows the number of different approaches and devices and really procedures that we have available for spine surgery. There may be cements, emerging technologies, disc arthroplasty, but the mainstay of our spinal surgery are the pedicle screw and rod constructs that we use in reconstructing the spine or realigning the spine. It is quite clear that there's an overuse of implants in certain societies. You need to consider carefully what you're trying to achieve with your surgery and whether an implant is really needed. There's massive marketing goes on, and in fiscal-based healthcare systems there's an over-treatment and over-utilization of metalwork. Our basic principles would be that we need to reconstruct the spine if we have destabilized it. That is, in fracture work, we might need to stabilize the spine. If we've done a large decompression, resection, or debridement for tumor or TB, we may need to stabilize the spine and reconstruct it. In scoliosis work, we're obviously realigning the spine and then holding it in that corrected position while fusion occurs. There are certain places where we might use replacement technology, such as disc replacement. To be honest, that's fading now. More commonly, we might use cages or anterior fusion assist devices, particularly in the cervical spine. Implant failure occurs either because of use of an inadequate implant or because of excess loading and a failure of fusion to occur. There are many different biomaterials that we use in surgery. There may be biological materials such as heart valves. We most commonly use metal, particularly stainless steel and titanium, in trauma work and reconstruction. And in the spine, we'll sometimes use polymers, ceramics, or even composites. Biomaterials may be bioinert, bioactive, or they may be biodegradable. It's a fundamental fact that all implants will fail unless they're either of adequate bulk and size, and so a fusion is usually an essential part of any construct that we use. Quite often we'll use a integrating biological solution rather than a fusion external to the implant. Certainly the implant should outlast the patient, and that particularly applies in tumour work. So on to some basic biomechanics. You should be aware of the stress-strain curve. This is where a material undergoes an elastic deformation. It then yields and starts to plastically deform. At a certain elongation and narrowing, it will fail, and that's the ultimate tensile strength, or UTS. In the human body, there's cyclic loading occurs, and for that reason, materials are usually tested with what's called an SN curve. This involves multiple loading cycles, usually for metals at about 1/3 of the ultimate tensile stress. It's quite a long and laborious process carried out in the lab, but it indicates the cyclic life under load of some of our basic biomaterials. This is a stress-strain curve for different materials of exactly the same geometry, and obviously to have a similar stress-strain curve you need the same geometry. You can see here that the stiffness is related to the deformation under load, and you can see that that changes according to the deformation. So titanium is somewhat stiffer than cobalt chrome. Young's modulus is how we quantify the stress-strain relationship and elasticity of materials. You can see here that cobalt chrome has almost twice the Young's modulus of titanium,